a member. I'm the BD at Veridise, so I'm more on the business side. That's why I need my script. And at Veridise, we specialize in delivering top-notch tools for automated security analysis through our innovative security as a service platform. Our suite of Veridise tools, which we developed in-house, is built upon cutting-edge research in automated program analysis, fuzzing, fungification, and static analysis. These tools are empowered our clients to uncover subtle vulnerabilities, enabling continuous integration and internal auditing of their ecosystem. Anyway, in this slide, we will talk about the bugs we found in zkEVMs and the audits we did for some zk circuits and the vulnerabilities we find in the zk circuits and zkEVMs. So, to start, what is a zkEVM? It's a layer 2 on top of EVM that scales transaction capacity. The way it works is instead of posting a transaction directly to Ethereum, you first run the transaction off-chain to obtain a trace, which is like a transcript of how transactions should run on the chain. Then you send the trace to the zkEVM, which creates a proof that your transaction is valid. zkEVM does this computation using zk circuits, which don't reveal the details of the transaction in the created proof. Finally, you post this proof to layer 1, which simply verifies that the proof is valid without running the transaction computation itself. So why does this scale? Because the layer 1 just needs to verify the transaction proof, which is much cheaper than running the transaction computation itself. So now you have a basic understanding of zkEVMs. I'm going to talk about how we can systematically find bugs in the zk circuits. So one effective and very popular method of systematically find bugs is fuzzing. We use two main fuzzing techniques, whole system fuzzing and trace mutation fuzzing. For whole system fuzzing, we're trying to find the traditional software bugs in the zkEVM. And for trace mutation fuzzing, we're trying to find the bugs more specifically in the zk circuits of the zkEVM. So in this slide, I'm going to talk about the whole system fuzzing. The idea behind the whole system fuzzing is to generate valid transactions for the zkEVM. Here's how it works. First, the fuzzer generates some valid transaction for the EVM. Then we generate a trace of the transactions on the EVM and send that to the zkEVM. Then the zkEVM tries to generate a proof. Since the transactions are valid, we expect that the zkEVM will always produce a proof. But if the zkEVM fails to produce a proof, that's a bug. This kind of bug could cause doubts, denial of service for users. A user could, send valid transaction to the zkEVM and get unexpectedly rejected. So this kind of fuzzing technique is unlikely to catch logical bugs in the actual zk circuits of the zkEVM. So far, we expect to just find traditional software bugs in the whole system fuzzing. So we used whole system fuzzing, and we find the bugs listed on the slide. We find 11 of them from the assertion violation to indexing errors and overflows. So those bugs I find from a zkEVM we audited before. but they're all fixed. So this slide, we are talking about more exciting fuzzing is trace mutation fuzzing. So trace mutation fuzzing is we use for looking for logical bugs in the zk circuits. So first, we generate some valid transactions for the EVM and generate the trace of the transactions. Then we actually send the trace to the zkEVM. We mutate it to introduce some inconsistency. For example, if the original trace contains 1 plus 2, we could mutate it to replace the 1 plus 2 with a random number. Since the mutations are just random meaningless number, the mutated trace probably shouldn't be valid anymore. So when we finally send the mutated trace to the zkEVM, we expect the zkEVM to fail to generate proof of it. But if we find a mutated trace for which the zkEVM does generate a proof, we probably find a bug. We will probably find a way in which the zk circuit is under constraint. In other words, the circuit has a loophole. So now you have a basic understanding of two Veridise bug finding strategies for zkEVMs. Next, I'm going to talk about Veridise tooling that we use for zk audits in general. Beyond just auditing zkEVMs, our main zk auditing tools are zk Vanguard and PICAS. zk Vanguard is a static analysis tool for finding common bugs in zk circuits. PICAS is a tool for formally verifying, so basically it's formal verification, that a zk circuit is properly constrained. So first, I will go into more details about zk Vanguard. So you give zk Vanguard two things: the witness generation circuit with the constraints and the list of detectors. Each of these detectors basically encodes the common bug pattern for zk circuits. Then zk Vanguard will analyze the witness generation circuit. zk Vanguard will either say that everything is okay or produce a list of warnings corresponding to possible bugs in the input circuits. Then the bugs could be like this: completely under constrained input or output signals, missing constraints for operators that developers commonly messed up, for example, like division, like also deviations between witness generation logic and given constraints. So to summarize, zk Vanguard is especially used for finding known vulnerabilities that commonly slip through when you're writing your zk circuits. Okay, this slide I'm going to talk about PICAS. So in contrast to zk Vanguard, which just gives you like helpful warnings, PICAS helps you formally prove that your circuit is sufficiently constrained. So at a high level, which is the only way I can understand it, you can use PICAS like this. You give PICAS an input circuit with constraints. PICAS will try to automatically prove there are no missing constraints. But if the circuit is missing some constraints, then PICAS will generate a counterexample, which is a specific input that the constraints mistakenly allow. In one sentence, PICAS is specialized tool with a very limited scope for these kind of proofs that it can do automatically. However, if PICAS does produce a proof, this provides a very strong evidence that the circuit is correct, because PICAS is a formal verifier utilizing formal verification. Okay. So Veridise, we actually we have been actively using PICAS and zk Vanguard, and have found them essential in numerous zk audits. Like these are the zk audits we did before. Rate limiting nullifier is spam prevention. It's a product from the Ethereum Foundation PAC team, and also Hydra S2 is from Sysmo. Meta network, telepathy from Saxink Labs, and also Unirep, also from Ethereum Foundation PhD team, Scroll, zkEVM, and also Circom library. So these audits reports are all public on our website. You can just scan QR code or visit our website later. Okay, these are the our methodology. These are the academic research paper detecting bugs in zk circuits. It's called Automated Detection of Under-Constraint Circuits in Zero-Knowledge Proofs. It's published in PLDI 2023. Sorry. In addition to the academic papers, we also have a blog which we write more approachable explanation of our research, as well as introduction to software verification and zk knowledge. You can check out blog later. Okay, these are our clients. Anyway, to conclude, I will give you a basic introduction to our major fuzzing techniques for zkEVMs and highlight two of our actively used tools for auditing zk circuits, zk Vanguard and PCAS. Right now, PCAS is open source and available at GitHub link on the slide, and zk Vanguard is currently integrated to our SaaS servers. Thank you. Yeah, I mean, feel free to let me know if you have any questions. I'm more on the business side, so if you do have some technical questions, I can, ask John. He's our CTO, and I will get back to you.
Thank you. Are there any questions? Thank you.